We really had to wait for the space age 50 years ago to really discover these objects in more details. And you have here some of these first images we had of terrestrial planets, Mercury and Venus by Mariner 10. Some pictures I found of the Earth in the 60s. And Viking 1 was the first really spacecraft to give us a lot of information about Mars. All right, so Voyager 1 and 2 missions were really inspiring and revealing all these outer solar system objects. I was young when these missions sent back all these images, and this is really something I remember as very inspiring. We discovered very much details about what's going on in the Jupiter's atmosphere, all these clouds and wears, and spots in many colors, even volcanoes on Io, and some interesting features on Europa. Recognize Ganymede and Callisto. Saturn, of course, and the Saturnian system. And one object I will be particularly interesting in my career is Titan. You see here with this veil of haze. Voyager 2 is the only spacecraft that really showed us anything about Uranus and Neptune, and I wish we can go there again sometime soon, hopefully. So now we have this this whole family of objects. They have been slightly reclassified recently, and so we have the 8 planets. 4 of them are giant planets, 4 of them are terrestrial planets. And Pluto and Ceres were put in a family called dwarf planets, which means that they are not the only ones on their orbits. And most of these objects are trans-Neptunian objects far away that we don't know much yet. But okay, and also we have all these family of satellites. So the bigger ones are orbiting Jupiter. Titan is orbiting Saturn. The Moon is our own satellite, and all the others orbiting mostly Jupiter and Saturn. Triton is orbiting Neptune. All right, so now we are going to focus on the atmospheres that surround some of these objects. So that's the layer of gas that is around the object. So we have different types of them. We have the giant planets, who don't have any surface and are their own class of large atmospheres. We have the terrestrial planets, and in that I will include Titan. I know it's not a planet, but I will talk about Titan as a terrestrial planet for the atmosphere from now on, because it's the only satellite that really has this atmosphere, this kind of atmosphere. Then I will briefly say some words about the other tenuous atmosphere we have, in particular around Pluto. But during all these courses, I will mainly focus, as I said, on the terrestrial planets, terrestrial atmospheres. So the giant planet type of atmospheres are thick atmospheres, mostly composed of hydrogen and helium. These planets, during their formation, kept these primordial hydrogen and helium from the proto-solar nebula. And they have a core of rock and ice, but mostly all the atmosphere is molecular hydrogen. As the temperature goes up and the pressure goes up when you go down inside the atmosphere, then you reach a transition where the hydrogen becomes metallic. So no surface, just a deep, heavy, highly pressured and temperature atmospheres. Uranus and Neptune are also mostly composed of hydrogen and helium, but they also include some methane. And the mantle, the interior of the atmosphere, is composed also with water, ammonia, and methane ices. So a little bit different. Terrestrial planets. So you have these. These are the terrestrial planets. I'm not yet talking about Titan. So the surface is visible for Mars and the Earth, and we see clouds and some things going on in this envelope of fluid around the surface. On Venus, clearly, it's all covered with clouds, but we can see and study the surface with radar in particular. And so I will focus more on these thin layers of gas now. The case of Titan. Titan is the only satellite in the solar system to have such a dense atmosphere, and these beautiful pictures were obtained by the Cassini spacecraft, and we can see that there are a veil of haze all around the planet. Also, the surface was not seen when Voyager came around, which was a surprise. And you can see some interesting features going on, like this detached haze, and this wonderful feature that appeared at the South Pole after the equinox. And so here the South Pole is entering winter, and this beautiful elevated cloud region appeared around the south, which is in fact an indication of some temperatures going down and subsidence arriving here. Now, a few words about the tenuous atmospheres. So here you have a picture of Io and a volcano erupting on Io. So there are some gas and some volatiles injected around Io all the time. It's a very, very thin atmosphere that will remain. And we also see on Triton some indications that there is wind. You can see that these streaks are indicated of materials ejected in and then blown by the wind. So there are some atmospheric activities, but these very thin layer of gas are more similar to what's going on in the very high upper atmosphere of the other planets. We had beautiful images and data from Pluto with the New Horizons mission, and you can see these haze layers hovering above the surface. And so this atmosphere is around 1 Pascal of pressure, mostly nitrogen, and very low temperatures. And you can see here in this rear view of Pluto the scattering by the haze, which extend apparently up to roughly 150 kilometers. All right, so for this tenuous atmosphere, I don't know much, and I will not discuss a lot about the processes, the specific processes that are relevant for these very thin atmospheres. Right, so let's have a deeper look at the atmospheric structures. So for the giant planets, here are some data that are relevant when you want to study the atmosphere of the giant planets. Of course, these are large objects, and there are one interesting point is they are rotating quite fast, faster than the Earth, around 10 to 20 hours. And this has an effect, of course, on the dynamics of the atmosphere. Another interesting point is the obliquity. It also governs a lot what's going on in the atmosphere. So Jupiter has no obliquity, no season, but Saturn and Neptune have quite similar seasons than on the Earth, with 25 to 30 degrees of obliquity. Uranus is a very specific case. It's tilted almost to 90 degrees, or more than 90 degrees in fact. It's meaning that it rotates in the other direction compared to Earth. And this, of course, has a strong impact on what's going on in the atmosphere, because you will light one hemisphere and then the other one. And it's something that's still, well, Uranus has not, because of the lack of data, not been studied much yet. So I will come back on the temperature structure, but as you can see, mostly composed of hydrogen and helium, and methane is 10 times larger in abundance in Uranus and Neptune than in Jupiter and Saturn. So there are clouds in these atmospheres, but they are not all the same. You can see Jupiter has a lot more colors and activity seen than the others. Saturn is more uniform in its band, but if you look closer, as Cassini did, well, you can see, of course, a lot of these activity also going on in Saturn's atmosphere. Uranus doesn't seem to have any specific feature. So again, we need to come back and look closer. And Neptune has some clouds and these large spot that reminds us of Jupiter's red spot. So there is also some interesting activity to monitor in Venus, in Neptune's atmosphere. These clouds are mostly formed in the troposphere, so in this layer where the temperature is going down as you get up into the atmosphere. Well, what we really call the atmosphere of giant planets starts at several bars of pressure, tens of bars of pressure. Below that, you're really in the deep atmosphere and you start getting something a little bit different in the way you study it. So starting at, let's say, 10 bars, we go higher and the temperature is going down. So we are in what we call the troposphere. Then all the planets are getting this transition with a minimum of temperature at the tropopause layer, which is always around 0.1 bar, 100 millibar. And then above that, you have the temperature rising again as you get up, and this is the stratosphere. So most of what we want to study for the atmosphere, which is similar processes, similar tools to study the atmosphere of giant planets, is going to be in these layers between tens of bars to 1 millibar and above. All right. So now the terrestrial planets and Titan. These 4 objects are really very interesting to study as a comparative planetology. They have some similarities, some differences. Many you can group them by 2 when you study one aspect, and it's not the same pair each time. So that's really interesting to really try to understand these similarities and differences. They also tell us a lot about the history of the solar system and the way Earth evolved this way and not Venus or Mars. So you have some data here, and I will start again with the obliquity. You can see then that Earth, Mars, and Titan have very similar obliquities, which means they have similar seasons. But Venus is like Jupiter, without any obliquity, no seasons. This 180 means that the axis of rotation is pointed downward, meaning it rotates in the retrograde sense compared to the Earth and the other objects. The rotation rate is an interesting factor. It's really it has strong influence on what we are going to study in the dynamics. And so you can see that Mars and the Earth have similar rotation rates, around 24 hours. While Titan, so one Titan day is one revolution around Saturn, because Titan is locked, showing always the same face toward Saturn. So one rotation around Saturn is 1 day for Titan, and it's 16 Earth days. And another order of magnitude higher is Venus, with 243 Earth days. I will make a note here about the fact that Venus has a rotation period which is in fact almost the same value as its revolution around the Sun. And since it's in retrograde rotation, the combination of the 2 rotations means that 1 solar day for 1 point at the surface, the time the Sun will come from noon to noon, is half of these values, so 117 Earth days. This is the relevant time scale as far as the thermal tides and the solar forcing on the atmosphere is concerned. All right, so slow rotation for 2 of them, which will be really a common aspect in terms of atmospheric activity. For the composition, we have 2 CO2 atmospheres, Mars and Venus, and 2 nitrogen atmospheres, the Earth and Titan. In fact, there is almost the same amount of nitrogen in the Earth and on Venus, but the CO2 that must have been present on the Earth too has been processed into the carbonates and is not present in the atmosphere anymore, hopefully for us. And while on Venus, the water was, the history of the water in the atmosphere is very different from what went on the Earth. And that ends up with these very large surface temperatures because of the greenhouse effect. I'll come back to that in another point. Composition. Okay, we'll see that for Titan, the methane has in fact a role quite similar to the water on the Earth in terms of hydrological cycle. So, yeah. So, no. Yes, the cloud cover. So again, we can group these atmospheres in two. We have on one side Titan and Venus, which are completely shrouded by these particles. It's not really, we'll come back to that of course, but it's not really the same kind of particles. We have on Venus what I will call clouds, condensate, and on Titan it's a photochemical haze. But the effect is similar. It will absorb most of the solar radiation, reflect most of it, a large part of it also, and absorb this radiation in the core of the atmosphere, high above the surface. And only a small amount of this solar radiation can reach the surface. This is completely different from the Earth and Mars situation, where you can see the surface and most of the solar radiation is reaching the surface, and the heating will come from the surface and not from the atmosphere. And Mars and the Earth are only partly covered with clouds, and this cloud activity is also related to the atmospheric activity and the composition, of course. All right, sorry. One particularity for Titan, because it's a satellite, or I don't know, but it's a smaller object than Mars and the other terrestrial planets. Its radius is 2,575 kilometers, and in fact, its atmosphere is very extended because of the low mass and low gravity, and surface pressure is high, 1 bar, 1.5 bar of nitrogen, but it extends. I mean, well, the exobase, so what we really see as the limit of the atmosphere, the external limit of the atmosphere, this exobase, which is around, I don't remember the value, but several hundred of kilometers for the Earth, Venus, Mars. On Titan, it extends to 1,600 kilometers, which is more than 50% of the radius, which means that the usual hypothesis that we do when we study atmospheres, that this is a very small layer of gas on top of the surface, and that we can deal with it as a plane parallel system. On Titan, this extension means that you have to revise all these approximations. And even what we see here, the haze layer, and the top of the haze layer is at 500 kilometers. It's already 20% of the radius of the planet. All right, the temperature structures. So here it's only a sketch of these temperature structure, except for Titan. Titan it's an observed profile. It's the Huygens profile that is represented here. All right, so you see that again they organize in pairs. This time it's the Earth and Titan, who shows a troposphere, a minimum of temperature, and then temperature is rising again. So they have a stratosphere up to a maximum of temperature, which is called stratopause, and then temperature is going down again in the mesosphere. On Mars and Venus, they lack the stratosphere part. You have a troposphere and a region which is called the mesosphere, but which is almost isothermal or slightly with a slight negative gradient. Around, so for Mars it's around about 50 kilometers, and for Venus also in the region within the upper cloud and slightly above up to 100 kilometers of altitude. Then above these mesospheres, you have the thermosphere. The thermosphere is a layer which is much more responding to the solar insolation. And you have large variation, very short relative time scales. And so that part is in its process will be that the pressures are much lower, and in its process you will get into a region where you have similarities with the tenuous atmospheres on the other objects I discussed previously. So usually I stop around the mesopause. Here is again the same temperature structure. This time these are observations. So you have some profiles in the Mars atmosphere. You can see the large variabilities. Of course, there is always large variability in the Mars atmosphere. It's a tenuous, thin atmosphere, and there will be a lot of variation due to the system and the solar heating. Okay. So, on the contrary, on Venus, the troposphere is very stable, extremely stable. And you have here several profiles of the probes that went into the atmosphere. And this temperature profile in the troposphere is this stability is indicating on a very efficient mixing of energy in the deep atmosphere. For the Earth, I didn't find a complete observed profile. I just show you two different regions. One is the mesopause on the upper left, right, and the other one is the tropopause region. Anyway, these are just examples to illustrate these structures. You can see on Titan, maybe one word about Titan thermosphere. You can see this nice structure that was observed by this Huygens probe in 2005. Again, for Titan, the troposphere seems to be very stable. You have large seasonal variations in the stratosphere region. I'll come back to that. This is an equatorial situation, which Okay, this is the equatorial situation in the winter, which is representative of most of the atmosphere, in fact, except the polar regions. And the thermosphere, you can see here this transition at 500 kilometers is very striking, and in fact it corresponds to the layer, the detached haze layer. So you're in this transition, you go above the haze, and then you have a different interaction, of course, with the solar flux. And you see these gravity wave propagating, which affects all the thermosphere profile, which is almost homogeneous in average, but varying a lot due to wave activity. So this is something that is very interesting to study. Now, some words about the current exploration, past and current exploration, but you'll hear more during this winter school, I guess, about all these spacecraft. The observation of the atmospheres started with the Venus transit, in fact. So in 1761, This Russian scientist, Lebonnois, studied the Venus transit, and he saw this transient aureola appearing next to the sun, and they deduced that Venus has an atmosphere. And he was right. This transit occurred also in 2012 and was studied again, but we won't see it anymore before 1 century. For Titan, a Spanish scientist, Camasola, suggested that Titan has an atmosphere because of this observation of limb brightening, and Cooper in 1944 discovered that methane was present in the reflected sunlight on Titan. But again, we really need to have space exploration to start studying these atmospheres, and these are the missions that went to study terrestrial planets and outer solar system. You can see that there is a favorite in there. You can't see all these names for the mission of Mars, but to Mars, but I'm sure you know most of them. It started long ago, and especially with the Viking spacecrafts. And now we have a bunch of rovers on the surface. For Venus, it started also in the same period, but it was more difficult to get to Venus surface and orbit and study this. Most of this information about Venus is really coming from Pioneer Venus and the Venera series of mission that went on during the 70s and 90s and 80s. So. The Vega 2 mission sent some probe inside the atmosphere of Venus, and in fact the Vega 2 probe is the only probe that really measured the temperature in situ down to the surface. The Pioneer Venus probes, the temperature sensor stopped working at 12 kilometers above the surface. So the only data we have for the temperature in the lowest 10 kilometers is coming from this Vega 2 probe, 1985. The Magellan mission was a radar mission, so we have a lot of information about Venus surface thanks to this mission. And then Venus Express is the European mission, very successful, that ended at the end of 2014. Lot of great data from Venus Express that you will hear about, thanks to Alessandro. And currently, so we have the Akatsuki, the Japanese mission. For the outer solar system, I mentioned Voyager 1 and 2, of course. There was also Pioneer Venus, Pioneer 10 and 11, and the Galileo mission. The Cassini is in orbit around Saturn. It's still in orbit. It will keep working until next year, near the solstice of Saturn. Huygens was this European probe that went into the atmosphere in 2005 of Titan. Sorry, and then we have New Horizons that went to Pluto and is going away, looking for other TNOs to look at. So the current missions are still in activity. A lot of missions are still in activity around Mars. Mars Express, Mars Reconnaissance Orbiter, this Indian satellite, Mangalyaan, that got into orbit in 2014. MAVEN mission is also doing a great job around Mars, and the Trace Gas Orbiter, European-Russian mission, got into orbit 2 weeks ago. Yeah. Unfortunately, without the lander. Still, Opportunity and Curiosity are still in activity at the surface. We will have 2 other missions soon. InSight, that was delayed a little bit, and the ExoMars rover. Hopefully, will land on the surface. So for Venus, we only have Akatsuki now. Akatsuki was scheduled to enter into Venus orbit in 2010 and do some coupled observation with Venus Express. Unfortunately, the main engine blew off during orbit insertion, and Akatsuki had to wait for 5 years around orbiting the Sun in approximately the same orbit as Venus, going a little bit too close to the Sun than expected. But still, the Japanese engineers managed to wait until they could come close to Venus again and try to another orbit insertion maneuver, only based on the thrusters. And this worked. So in December 2015, they managed to get into orbit. Of course, it's not the expected orbit, but it's much. They expected a circular orbit, almost circular, to study the superrotation and get some rotate simultaneously to the flow for a while, to really study the superrotation on Venus. Now they are on a very eccentric orbit, very, very eccentric. The apocenter is very far away, but still they can do a very good science, and all the instruments survived the 9 pericenter pass close to the Sun, and now they're already showing some interesting results. So it will be very exciting to follow this mission. Hopefully we'll have another mission to Venus soon with some projects, discovery projects at NASA. Go Da Vinci. For Jupiter, we have the Juno mission, which is in orbit right now. That will be studying the Jupiter system. And Europe will go also to Jupiter very soon with the JUICE mission. So, but the space missions are not the only exploration we can do for the atmospheres, the only information we can rely on. We have a lot of ground-based and space-based telescopes that help a lot now also to study the atmospheres. On the surface, we have large telescopes, the VLT, or the large instruments, telescopes and instruments at Mauna Kea on Hawaii, and the newly ALMA radio telescope network in Argentina. And from space, we have the Hubble Space Telescope, which will be retiring soon, replaced by the James Webb Space Telescope that will be launched in 2018. I also illustrate here CoRoT and Kepler spacecraft. They are mostly studying the exoplanets, not our solar system, but we can have some interesting information now about these faraway worlds. And there were also a lot of several observatories, space observatories in different wavelength range. For example, the EUE, UV Explorer, ISO in infrared, and Spitzer, which is still observing in the infrared, far infrared. And these telescopes and observatories are very complementary to the space missions as far as atmospheres are concerned, because of course you do not get the same spatial resolution from the Earth than going close to the objects, but you can rely on extended observation periods, and this is interesting when you want to study seasonal variations. You cannot, well, Cassini has been very long around Saturn and covered almost half a Saturnian year. But it's difficult to get long period of observations with the same instruments with a space mission. But you can get it from the Earth. And we now have very long time series for seasonal variations of Titan atmosphere, for example, thanks to the observations from the Earth. The instrument technology is not exactly the same, and also the type of instruments. You cannot send the same type of instruments on a probe than you can build on the Earth or on a space observatory. And the technology, when you go to the outer solar system, it's always a long delay before you reach there, so the technology is not the same as what you can get on Earth. So there is a shift. All this means that these explorations are really very complementary. And we need to keep efforts on both sides to get all the data we need to study the atmospheres. All right, I still have a little bit more than 10 minutes to talk about other stellar systems. So, in the last years, we've been discovering lots of exoplanets, and this is really a field that is expanding very quickly, and we have, I think, as far as planetary atmospheres are concerned, we have a lot still to learn about our own solar system atmospheres, and but the picture we have is really I mean, we understand a lot of things about what's going on, and now we need to look at something wider, a wider picture. We have a good sample of atmospheres very close to us, but we have a lot more atmospheric system that waits to be studied in a more statistical way with all these exoplanets. So these are a lot of potentially habitable exoplanets. You can see the size, the relative size, I think, are correct. So between the Earth and Neptune, you have a lot of different types of objects around different type of stars, and these exoplanets can be discovered by many techniques. But you can see on this plot that the two dominant techniques are the radial velocity, which means you study the Doppler variation in the spectrum you receive from the star. The Doppler effect that is induced by the variation, by the movement of the star on the relative to the gravity center of the system. That means that when you have a heavy planet close to the star, you will get a wobble of the star, and this shows up in the spectrum, and you can get the characteristics of the planet this way. This is, of course, biased towards heavy masses and close objects to the star. But it's a technique that is really efficient. The other technique, which really exploded recently, is transits with the Kepler mission. We discovered a lot of planets. This for this you will look at the planet as it goes in front of the star, and dim a little bit the light you get from the star. So this regular dim of the light of the star will give you some indications on the planet. And then you have a lot of more interesting details you can get on the light curve. So this technique is also a little bit biased towards close objects to the star. So you have a lot of green on the left side of the plot here. As I said, most of these planets have been recently discovered by the Kepler telescope. And so if you keep up going on, we can discover a lot of objects. For the there are many types of planets, groups of planets that can be separated in this whole sample. You've got the hot Jupiter, which will be very close to the planet, very high equilibrium temperatures, very large radius. So very large objects that are close to their stars. But for the interesting potentially habitable terrestrial-like atmospheres, you have to look at what's going on with a temperature equilibrium in the range of 200 to 300 Kelvin, and masses around the Earth one, and maybe as high as 2 to 3 Earth masses. But still, this is a small box, but you still have a lot of objects in there. Now the most interesting one will be in what we call the habitable zone. This habitable zone is defined by the fact that you can get liquid water on the surface of the planet. And this has a lot to do with the distance to the stars and the amount of energy received from the star. So the Earth is either ideally placed in this habitable zone around the Sun. The limit of this habitable zone are a little bit subject to discussion. It depends on how you model this, what's going on in the atmosphere. And for a long time, it's been studied only with 1D radiative convective equilibrium models, which gives only a very simple energy balance question. These limits given by these simple models have been revised since we do 3D general circulation models now that can really show the impact of the cloud coverage and the circulation, 3D circulation around these objects, depending on whether they are locked in phase, looking to their star if they are very close, or in a different kind of configuration. And this can show that the clouds can really change the picture you can get on the surface temperatures. So you will affect these limits of the habitable zone, both outer and inner limits, quite significantly depending on what you can study with these more evolved models. So, but okay, we also can think about what the evolution of Venus, and maybe Venus was in the habitable zone someday or went away. The habitable zone is also something that evolves with the age of the star. The luminosity of the star has been evolving a lot since the beginning. It was much more active. The amount of energy we were receiving at the beginning of the Earth history was 25% more than today. or less, sorry, less, 25% less than today. And but with more active UV and high energy photons. So these differences, this evolution of the solar radiation will affect also the time the planet will stay in the habitable zone. This is a field that is really, as I said, expanding, and that will be a lot of interest. And the more planets we can discover in this kind of region, and if we can get some hints of the atmospheric conditions there, then we can refine our understanding of this habitable region and where to look for life as we know it. So atmospheric hints, we can already have some hints about the atmosphere around some of these objects. You have here some examples of infrared spectra that were obtained. The first one by Hubble. The second one I don't remember. Sorry. So you have some in, I think it's Spitzer, the second one. Spitzer spectrum. And so you can see that with these points, of course, it's not a high-resolution infrared spectrum, but we can get some hints of on the atmospheric characteristics with this. This spectrum is obtained as you see the difference in the light you get from the star as the planet transits in front of it. And so on this plot, you have, in fact, a model, a 3D general circulation model of what could be going on in this type, in this GJ1214b planet, which is a mini Neptune, slightly smaller than Neptune, but larger than the Earth. And it's the model. You can see the red is the type of atmosphere you can expect without any cloud, and you can see that there is a lot of signatures in this region that we should be able to see. If you don't want to see any signatures, which is the case, the spectrum is almost flat, then you have to include clouds in the atmosphere, and you can even have information about the size of the cloud particles. So you can really get already now some informations about these atmospheres and try to start speculating and modeling these kind of objects. Same thing for this other Spitzer spectrum. You can see that there are indeed spectral signatures in the spectrum. The cloud-free model is a little bit too deep, too large variations, but this other blue model is too flat. So you have a best fit model in the between, and then you can get some information about the amount of water and possible cloud coverage of this object. So this is really a wide field that will be expanding in the next few years. So that's your generation of exploration. And you can, as far as planetary atmospheres are concerned, there will be a lot of fun going on in the next years on these objects. And I will stop here for this one. And tomorrow I will talk about radiative transfer in a little bit more details. Thank you very much. Any questions, maybe? I don't know.
Are there any spectra of exosphere-atmosphere compositions?
Composition signatures? I'm not sure. I don't think so. Not yet. But something that is possible to... I mean, we could, in this kind of spectrum, we already have some information. I don't know if we have any more extended data sets. it's mostly covering the near infrared spectrum, and not that I know of.
Yeah, well, I'll just talk loud. Oh, yeah. Hello. Okay, so I wanted to ask on Titan's atmosphere. Can we go back to your plot on the Titan? You had the pressure versus temperature profile. I was curious why. Well, we'll just wait for the curve. You said it was above the, yeah, right there. So above 500 kilometers, you said that's above the haze layer?
Yeah.
Right. So there, the dotted line shows what it should look like, but then the data
the
shows...
dotted line is a model. Well, it's a model done in 1991 by Emmanuel Lelouch. It was based on measured temperature in the upper thermosphere at 180, and then taking into account all the non-LTE stuff going on in this region, you could get something going back to this isothermal region, and with this minimum in temperature. In fact, this point at 180 Kelvin was revised. These UV observations were revised. Voyager, it was UV Voyager observations. They were revised, and they got a temperature that was much smaller, 155. But you still can get a model getting a mesosphere up to this temperature and a minimum of temperature somewhere. But okay, this is the observation, so it's not the model.
Mm-hmm. So the isothermal profile that's going up like that is due to ultraviolet heating?
Yeah, there is a lot of ultraviolet heating and non-LTE processes going on there. The composition is, I mean, now we have a lot of data sets about the exact composition of what's going on in this upper region. So models can be refined. And there are now three-dimensional thermospheric model to cover this region, but it's not easy to model this temperature structure.
Thank you.
Why there are so many profile lines of Mars?
Sorry?
Why there are so many profile lines of Mars in that?
These are different examples of profile. I have to think. I forgot what this is. These are Mars reconnaissance orbiter, I think, profiles. But there are several ways to get temperature profile. I don't remember if it's radio occultation or stellar occultation to get these profiles. I have to check. But there are many possibilities to observe temperature profiles with all the spacecrafts. And these are just a couple of examples from Mars reconnaissance orbiter, I think. It's very variable with the season and with the latitude and with the position and our local time. The atmosphere of Mars is extremely variable in terms of temperature. So.
In the case of Venus and Titan, where we have actually in situ measurements, how well are the in situ measurements in agreement with what you can derive from remote sensing? Are they making sense, or are they completely different?
No, they are in good agreement. So you mean just for the temperature profiles like this?
Yeah, for instance, because here this curve on Venus, I mean, I don't know here if it's derived from the Venus Express remote sensing.
No,
or from
these
the
curves
Venera.
are probes, so in situ measurements.
Okay.
These are in situ measurements. But with radio occultation, for example, you can measure the temperature down to the cloud, bottom of the cloud. You cannot get information with radio occultation, nor with any stellar occultation, because of the cloud layer. So usually you stop at 30 to 40 kilometers. But above 30 or 40 kilometers, above 40 kilometers, the temperature structure you get from radio occultations is is in very good agreement with all these in situ measurements. For Titan, we only have one profile in situ, and it's also in quite good agreement with the retrievals from infrared observations and radio occultation. The position of the stratopause, in fact, is not completely in agreement between this profile and the profiles retrieved from the Sears infrared instrument. You can get the temperature from Sears observations in this stratopause region, and the stratopause observed by Huygens is a little bit lower than any of the other observations. But there are some, I mean, you can go into the deep, small differences, but usually it's in good agreement.
Okay, we are on time, thanks. Now we have the coffee break. Coffee break is going to be in the library. The library is